Okay, hi. So, in this interview, I will be trying to solve problem 122 on Leetcode, best time to buy and sell stock, number 2. So, I'm given an integer array prices, where prices of I is the price of a given stock on the ith day. On each day, you can decide to buy or sell the stock, and you can hold at most one share of the stock at any time. However, you can buy it and immediately sell it on the same day. Find and return the maximum profit you can achieve. Okay, so some immediate notes that I'm noting is that first of all, you can hold at most one share of the stock. This means one thing. At say like the ith day, you either have a stock or you don't, right? And that means that starting at the 0th day, you don't have a stock, but you have the option to buy it. And that means that if you have like already hold a stock, you can't buy it again, right? So this immediately tells me that there's only two states that a customer can be in. One state is in which you have the stock, and another state is in which you don't have the stock. Now, if we notice how these states transition to each other, well, you can obviously buy or sell it, right? So that means that the act of buying a stock transitions from, say, state 0. First of all, let's just say state 0 maps to, let's say, not having the stock. And state 1 means that you have the stock. So these are the two different states that we're denoting by 0 and 1, and that means that buying a stock converts from not having the stock to having the stock. So it goes from state 0 to 1. Similarly, selling the stock goes from state 1 to 0. And then there's a third type of action. It means that you can buy it and then immediately sell on the same day. So we also have this simultaneous, like, say, two-step transaction that goes from buy and sell, which is a transition from 0 to 0 itself. So since we have, say, like two possible states and an array of prices, what immediately jumps to mind is, say, like a dynamic programming approach, where we can say, like, define, say, some function f of I j, where j exists in the range from 0 to 1, and f of ij returns, say, like the maximum profit that you can obtain ending at the ith day, where j represents whether or not you have the stock. And we can say that a dynamic programming approach works here because say, like, if you have, say, like some optimal price up to some certain day, then it is obvious that that must also depend on some previous optimal state. And we can say, like, for example, if we consider, say, dp of ij is equal to max is equal to dp of I minus 1. Let's just say, like, okay, let's just, for example, consider the state of having the stock. The only way you can have the stock is if you buy it, right? So you either already have it, which is equal to dp of I minus 1, 1, or dp of I minus 1, 0, minus the cost of the stock, so it's cost of I, right? Immediately, we can just notice that, first of all, depending on what dp of I minus 1, 1 is, dp of I minus 1, 1 must be, say, like the maximum profit you can achieve on the I minus day while having the stock. Like, you can just do this with a simple reasoning, say that if it was not the maximum, then we can just, take the maximum value, and dp of I minus 1 must therefore always be the maximum value. Same thing with dp of I minus 1, 0, and cost of I. Since cost of I is constant, we want to maximize this value, and this stands to reason that, say, dp of I minus 1, 0 must always be the maximum profit available on the I minus 1 day while not having the stock. and there can be no other way. So we can recursively formulate this as say dp of ij is the maximum profit depending on say like the state of the stock at that time. And yeah, and that's where like say the reasoning for this dp approach comes about. So this is for dp of I1 is equal to dp of I minus 1 1 or dp of I minus 1 0 minus cost of I. And we're going to take the max over this. This then furthermore means that we have to define dp of I0, which is also either going to be dp of I minus 1 0, which means that we stay not having the stock, or is going to be dp of I minus 1 1, the state where on the previous day we had the stock, and we sold it, so plus cost of I. Or we can say dp of I minus 1 0 plus cost of I minus cost of I. In that case, this is the action of say selling or selling and buying on the same day. So now that I have this approach, the overall time complexity of this, considering that say like first of all, we have dp of I0, which means that we have say like n by 2 states, or overall say like 2n states, or O of n transitions, where each of them depends on about like say like 2 or 3 previous states. So overall dp time complexity here is O of n. Yeah, I don't believe I'm missing anything. So these, I think I covered all cases. You can buy or sell on each day, right? And you only can have one stock each day. So you can just simply define dp of ij as say like on the ith day, whether or not you have one stock or you don't have a stock, the maximum profit at that state. So I think that overall works. I will start to code this now. So let's say dp is equal to, say it's initialized as 0 for range n, and n is going to be length of prices. Okay, so initially you can say either sell the stock immediately. So you can say dp of 0 0 is equal to max between 0, or you can say buy and sell immediately. So price is 0 minus wait, so if you buy and immediately sell on the same day, it's the same thing as just not doing anything with it, no? Yeah, I guess. So it's still going to be 0 regardless. dp is 0 1. It's going to be negative 1 times prices is 0. And then we're going to iterate from 1 to n minus 1. So then dp of I0 is going to be equal to next between dp I minus 1 0 and dp of I minus 1 1 plus cost of I. Means that you sold it on that day. And dp of I1 is going to be max between dp of I minus 1 1 or dp of I minus 1 0 minus cost of I. So it means that you bought this. And that means that then you can Then return the max speed dp of n minus 1, 0, dp of n minus 1, 1. The only thing that's tripping me up slightly is that you can buy it and then immediately sell on the same day. But that's essentially like a transactional cost of 0, so you might as well not have like done anything at that point. So I think it just comes down to say like the same. Oh, right. Oh, it's not cost, it's prices. And so far it seems to hold up. Okay. So far that approach works. Now, the time complexity and space complexity is slightly concerning. Is there any way that we can optimize this? Maybe it could be something to do with, say, like the two-dimensional DP of this. Maybe only one-dimensional is enough. Like, for example, oh yeah, some of these use just 0 milliseconds. Should just give me O of n here. Yep. Maybe we don't need to keep this inside the array. We can just say, like, for example, keep it as constant space, since we're always, say, like, we only need, say, like, the previous, like, say, state of having the stock or not having the stock. So in this case, we could just use, say, like, O1 memory. So we can just have two variables, one of which is, say, like, not have equal to 0. Have is equal to -1 times prices of 0. And instead of that, we can just say not have is equal to max between not have or have plus prices of I and that gets rid of this. You can say new have is equal to max between have and not have minus prices of I, right? In this case, we can then say, okay, not have equals to new not have equals to new have, and then we can just return the maximum between now have and have. Right, in this case, we can just limit the memory complexity to O1, since we're only maintaining two variables. And that does beat the runtime complexity a lot more. Still using 3 milliseconds though. And we are having, say, like O1 memory, which beats 90%, which is pretty good. Okay. Maybe having while loop versus for loop matters. I equal to 0. And we can try while I is less than n. I plus equals to 1. Oh, maybe that will do it. Does use up. Oh, it doesn't do any better, but does use up more memory. Not sure. Curious how these it is time complexity of n. Oh well, this is probably good enough.